So what we're looking at for this scenario is how can we use the either addition or subtraction properties of logs to be able to rewrite my equation as a single log, so that I can then apply either of the two guidelines we have above. That's what we're kind of hoping for in this, in what we're looking at for these examples. So all I've done here is rewrite both the sum and the difference identities or properties of logs for you. So remember that if I am adding two logs together, I can rewrite them as a single log with their arguments multiplied. Or if I'm subtracting two logs, I rewrite them as a single argument with their arguments single log with their arguments divided. So we're going to use those two concepts to be able to solve three equations in this set. In each of these equations that I solve, I want to not only find the exact answer, but that approximate answer from my calculator rounded to 3 decimal places. So the first example we're looking at says log base 2x, or log base 10, or log of 2x minus log of x minus 3 is equal to 1. And you'll notice that I can't use the very first scenario we started with. In other words, I cannot rewrite this as in its exponential form because I have too many logs here. I can't apply the one-to-one property because I have this 1 over here. So what do? Well, this is where we're going to apply the difference property of logs to transform the left-hand side into a single log expression. So because I'm subtracting here, that means that I can take the log, log, and rewrite this with the first with the numerator being 2x and the denominator of x minus 3. Set that equal to the right side, which is 1. So now that I have a single log equal to a number, I can just rewrite this using the definition of logs, or rewrite it in its exponential form, which gets that variable x out of that kind of hidden argument position. So this is an log, which means it's a log base 10. So this is 10 raised to the first power, equal to the argument of 2x over x minus 3. If I were to multiply both sides by x minus 3, that gets rid of the denominator over here on the right, and I end up with 10 times x minus 3 is equal to 2x. Distribute the 10 to remove the parentheses, and I get 10x minus 30 is equal to 2x. I'm going to subtract 2x over here to the left to get 8x, and I'm going to add 30 to the right to get 8x is equal to 30. Divide both sides by 8, and I find out that x is equal to 30 over 8, or 15 over 4. And that's the first example that we have for this set. Now let's look at a different example. For this one, I have log base 2 of x plus 1 plus log base 2 of x plus 7 equal to 3. Again, I can't rewrite it as a single log. I can't use the one-to-one property because I have the 3 in here. So I'm going to transform the left-hand side into a single log to set equal to the number 3. So I have log base 2 of the first argument of x plus 1 times the second argument of x plus 7, and set that equal to 3. Again, I rewrote the left-hand side as a single log, and so now I'm able to rewrite this entire equation from the log and change it into its exponential form in order to get the variables x out of that kind of hidden argument position. So the base here is 2 raised to the third power is equal to the argument of x plus 1 times x plus 7. And we go on from here. So this is going to end up being 8 equals, and I'm going to expand the right-hand side over here, or FOIL it, so I get x squared plus 8x plus 7. And so I have a quadratic equation. To solve our quadratic equation, we want to make sure that we set the equation equal to 0 and solve. So I'm going to subtract 8 from the left-hand side, and I get 0 is equal to x squared plus 8x minus 1. So I know already that this thing doesn't factor, but instead I can solve it using the quadratic formula. So remember, when we use the quadratic formula, x would be equal to negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. Simplifying underneath the radical sign that I have up there, I get negative 8 plus or minus the square root of 68 all over 2. So 68 is actually 4 times 17. So when I simplify the square root of 68, I get negative 8 plus or minus 2 square roots of 17, all divided by 2. From here, I can reduce that fraction even more because 2 divides into both the numerator components up there, and I end up with negative 4 plus or minus the square root of 17. So that's where I would initially stop, or at least I've stopped up until now. But remember that our argument has to always be positive, right? So the argument here must always be positive. That was part of the rules that we've stated before. And the variable x is in the argument, so I have to check whether or not these two solutions cause either of those two arguments up there to become less than 0. Okay? So negative 4 plus the square root of 17, whatever number that would be, and negative 4 minus the square root of 17. So we need to see what that decimal value is to know whether or not we throw anything out here. So if I were to figure out what negative 4, so negative 4 plus the square root of 17 and negative 4 minus the square root of 17, so one time I get, we'll call it 0.1, and one time I get negative 8. So negative 8 plus 1 is going to give me a negative value, and negative 8 plus 7 is still going to give me a negative value. So that number doesn't work for us, but the other option that I had was just a positive 0.12. So positive plus a positive. So out of the two options down here, the only answer that survives is x equal to negative 4 plus the square root of 17, and that's the exact answer. And the approximate answer is going to be 0.123. 0.123. So just to be clear, this answer here without my calculator is the exact, the one with the calculator is the approximate, and those are the solutions to this equation. Now the last one that I want to look at together in this grouping is going to be this one, x log base a of x plus log base a of x minus 2 is equal to log base a of x plus 4. I have 3 logs in this equation. So what I need to do is try to condense it down as easily as I can. So on the left-hand side, we can actually rewrite the left-hand side as a single log. Remember, if we are adding 2 logs of the same base, then we simply multiply their arguments. So this would be x times x minus 2. Set that equal to log base a of x plus 4. So this time we were able to rewrite the left-hand side as a single log, and now what we have is log base a equal to log base a. So we can actually use the one-to-one property on this because our bases are the same by setting the arguments equal to each other. So x times x minus 2 is equal to x plus 4. And we solve from here. So just simply removing the parentheses from the left, I get x squared minus 2x is equal to x plus 4. Again, I have a quadratic equation, so I'm going to move everything over to the left and set it equal to 0. So I get x squared. When I subtract x, I get minus 3x, and I'm going to subtract 4, setting it equal to 0. This looks to me like it will factor, so we'll try to factor it into an x and an x equal to 0. Because this is a negative, I have to have positive and negative signs. So I need a negative 4 plus 1, which gives me back the negative 3. Setting each of these two factors equal to 0, I have x plus 1 equals 0, x minus 4 is equal to 0, or x is equal to either negative 1 or a positive 4. So once again, we have to go back and check, do either of these possible solutions not apply because they cause the argument to be negative? And we can see here that negative 1, if I were to substitute negative 1 into that very first log expression, would cause, of course, the argument to be negative. So negative 1 does not count. So the only solution that we have here then is that x is equal to 4.